All right, so in this video I wanted to talk a little bit about distributed loads and how we simplify them. So in your picture, in your book, when you see a picture that looks like this being a beam or some sort of piece of steel or a wall or whatever, and you see a force being indicated with this type of sort of notation instead of a very distinct and discrete point force acting either down or at an angle. This is what we would call a distributed load. The idea is that instead of a specific force, like say 20 newtons acting at a very localized location, like a point force, we have like a bunch of stuff just spread out over the length of the beam. So it might be like a pallet that's loaded with bricks, or maybe a pile of wood, so that there's weight acting everywhere. And so the question is, how do I simplify this, or how do I deal with this? So when we see something like that, again, here's our beam, and it might have, say, a rectangular shape. And here, they might say, they call this W of X, which really indicates that it's called the loading function, which in this case, because it's just a horizontal line, might just represent 2 kilonewtons per meter. It's always going to be in the units. If we're talking about a two-dimensional picture, it's always going to be in the units of force per length. The idea being here, for instance, that maybe this beam is 4 meters, and so it's somehow related to, the amount of force that I end up having is going to be related to this loading function, and then of course how far it extends over. Well, if W of X is the force over the length, then essentially we would want to multiply by the length in order to get the total force. In a more general way, when allowing for the case that perhaps our loading function isn't a straight horizontal line, maybe it's an incline, or maybe it's some sort of curve that we were given a functional relationship for. How do we find the force? The force is going to be equal to the loading function integrated over the entire length of the beam, or where it's acting. And when I look at that and I sort of put this in context to this picture, it's really just the area under the W. It's just an area, So it makes it kind of easy to say that for this particular picture, the total force would be 2 kilonewtons per meter times 4 meters is 8 kilonewtons. So the total force that this beam is experiencing is 8 kilonewtons. The next question that we're going to answer is, well, where do I put it? Because as we're going through this chapter 4, we're also realizing that not only does this force create a force downward, we can also think about the moment that it might be creating about a particular point. If I push down on this beam right here and it's fixed here, there's going to be a moment about the end of that beam caused by that force, and it depends on how far away it is. So where I put it matters. So the answer to the question is that it's put at the centroid of the area, which is really a way of saying the center of area, the geometric center, sort of similar to the center of mass. For a rectangle, again, answering that question like, well, where is that, is pretty easy. The centroid of a rectangle is at the center. And so I could replace this particular picture. I could redraw it. Here's my beam. It's 4 meters long, and there's an 8 kilonewton force acting 2 meters from the end. This is the exact same as what we started with, but I've drawn it more simply. Other shapes might be more difficult, but there are some that we can kind of remember pretty easily. For instance, a triangle. Now, where do I draw the centroid of a triangle? Well, if this is the base, the centroid of the triangle is right here, and the distance here is 1/3 of the base. It's hard to see that that says 1/3, isn't it? 1/3 of the base. So I always remember that the centroid is going to be skewed towards the fat end of the triangle, and it's 1/3 from that fat end or 2/3 from the skinny end. If you can't remember it, it turns out that there are some really helpful pictures in the inside covers of your textbook. If you don't have a hard copy, it's also on a digital form, but it gives you common geometric shapes and where their centroids are. And so that is a way that we can also draw that. But in any case, if I had a loading function like this, I would still find the total force by finding the area of the triangle, and then I would place that total force that I got 1/3 of the base away from the right-hand side of that triangle. Now finally, the last possibility that we might have is, what if we have a situation where our loading function is some function of x, like maybe it's 4 plus 3x squared minus 2x. I don't know what that curve looks like, but you know, how would I find the total force? I would still do the integration. So the total force would still be the integral of this and I can do that if I know how long the beam is. It's fairly easy to find. Now, how do I figure out the x? Well, let's draw a picture here. So let's say that our curve looks something like this. Now, if I imagine a little piece of it if I just took a little strip of that, that would be providing a moment that would be equal to w of x times dx. That would be the little moment that it's equal to. And if I integrate this entire thing, it'll give me the total moment. Oh, I'm sorry, I need an x here. All right, so what I really meant to say is this little piece right here, if I'm thinking about the force that it provides, if I just take this little sliver of my weight that's acting down on the beam, and it's a distance x away from this end, the force that this applies is just equal to w of x times that width dx. But then I multiply it by x to get the moment that that little piece creates. If I integrate over the entire length of the beam, that would give me the total moment that all this force creates. And the idea is that I'm trying to figure out, you know, what's the total force times the proper location of where I could put a single force, and where would I put that x, where would I put it to create the same effect as what I calculated the total moment to be. Does that make sense? So we're saying that if I do this integration of this strange curve, just so I know how to deal with that, I would find the total moment would be x times the force. So instead of just doing this integral, I'm taking x times the w of x and integrating it. So that's the total moment due to my distributed load. I want to replace that by a single force, which I know what it is. It's the integral of the distributed load over x. And I want to put it at the right location. So x bar, where I want to put it is the total moment, which is this integral, over the total force. And the total force, of course, is just that integral of w of x dx. We don't have to do it too much, but that is how we would find the place where we want to put the point force if we wanted to replace this picture by a single force put at the correct location. Okay, so distributed loads are going to come up sort of throughout the course of this first half of the class, and so we wanted to know how we would deal with them.